Do you hear me online or not?
Yes.
Oh, I need sound. Okay. Can you repeat? I didn't have sound. Okay, can you hear me online?
Yes. Yes.
Okay, perfect. And can you see the screen as well?
Yes.
We'll also try to keep with the chat. Actually, maybe let's do that again. So I'm gonna extend it. I'm gonna use this and share this. And I can see the chat here. Okay, online, if you have questions, don't hesitate to ask directly or use the chat or whatever. Okay, let's start. So today we'll talk about image classification. So normally last time you've heard about the basics of neural networks, and so here we'll focus on images. So what is so here's the outline. So like a bit of motivation about what is image classification and why is it useful. Then we'll talk about the framework and how to do classification or some ideas about classifications. Then we'll talk about convolutions, which is an improvement over the first framework that we're going to talk about. And then a quick overview of datasets and models that exist. And then we'll go to the practical session. So first, as an introduction, what is computer vision? So you all know about vision because you experience it yourself with your eyes. So you have things that happen, and your eyes is like an image sensor. And so you can understand the world around you by seeing what happens. And so computer vision is to do exactly that, but with a computer. So here the sensor is not the eye, but so here is a webcam, but a camera. And we'll focus on still images, so not video, but images. It's already quite complex, quite hard. And you can have different kind of tasks. So for example, the classification task where you have an image like this and some categories, so list of categories. So here are several objects and animals. And the goal is to find which category is best suited for the image. So for instance, here it would be skateboard among the other ones. So of course, there are many objects in the scene, but because we have a restricted list of objects, the one that fits the most is skateboard in this case, and that would be our target. So this is image classification. Another kind of task could be object detection, where you don't only where you have localization first. So where are different objects? So here you need to put like this rectangle box around each object. So here, and you also have classification of each of the objects. So here would say like this is a human, this is a skateboard, and so on. So it's a bit harder task because you also have the localization added. And you could also have even more difficult task, which is image segmentation, where now you also have to really like give a precise bounding box, a precise contour of each object. And so today we'll focus on image classification, and you'll see image detection and image segmentation in a future lecture. And this is particularly interesting for you guys because I think you you could work with this kind of images where you would have let's say like a brain scan with some tumor, and in particular image segmentation could be like to define to localize where a tumor could be, or So this is image classification, image segmentation. Image classification could be just like have a brain scan and say whether there is a tumor or not. So yeah, we focus on image classification today. And so what is image? So I'm going to give more detail about image classification because now I've told you like we work with images, but computers don't really see, right? You have a camera that takes images. How does the computer see? We're going to talk about this. And then you have to transform this somehow into a list of targets. So here it could be a list of categories, dog, cats, and car, and you have to find which one is the correct one. So for instance, here say that, okay, cat is the good one is cat and the other one are wrong. Sorry about this. Is it? Okay. Okay, so why is this a problem? So first of all, an image is, well, for computers, there's just pixels. And the pixel is represented as a RGB value, so red, green, and blue. And so each point in the image, each pixel is actually 3 numbers. And so what it means, so 3 numbers that represent one color. And so what it means is that an image is actually these RGB matrices, so like lots of numbers that represent each pixel in the image and their values in red, green, and blue. And so actually, so we don't really go from images, but we go through these kind of matrices, and we have still the same task where we need to find which category the image is representing. And usually you don't actually want to say this is a cat and it's not a dog or not a car, but you want some kind of probabilities or certainties about each category. And so you would go from this image and say that, okay, there is 82% certainty that this object is a cat, but still 9% chance that it could be a dog, and then so on. And this comes with a lot of challenges. So of course you have images of cat, but the problem is you could have several viewpoints. So you could have a profile of a cat, you could be facing the camera, or you could see its back. You could have different kind of illumination. So it could be night or day. Also different kind of deformation due to your camera sensor. So you imagine you have some dirt on the lens, or if there is some kind of deformation. You could have occlusion. So here we only see the tail and the main part of the cat is hidden. Clutter here is that we have an image with a lot of high frequency detail, and it's very hard to segment the cat because of all of the clutter in the image. And also, of course, each class could have a lot of variation. So one cat, the cats have the variation in color, in texture, and so on. So when you design your object classification model, you need to take into account all of this. And this makes it challenging. So we're going to look at a small little framework or introductory framework for image classification. And so now to do that, we're going to talk about functions and inputs and outputs. So our image would be the input of the function. The classification model would be the function itself, and the different probabilities for each class would be the output. So we want a function that, given a feature representation, so here in this case an image, gives either the category or just probabilities. And so this is how you would typically write it. And this is probably what you talked about a bit in the previous lecture. So how to do that with neural networks. And in machine learning, the main approach is to do it so data-driven, which means that we don't assume anything about the image or what we have, but we just have a lot of data, and we're gonna infer the correct function from the data. And so for that, we need a big database of images, and we also need the labels. So lots of images of, let's say, cats with labels saying cat, lots of images of dogs with a label dog, and so on and so forth. And then we're gonna infer, or what we say, learn or train a model that can find the correct label from an image. And then at the end, we need to evaluate how good our model is performing. And so we need, so usually what you do that, so how we evaluate each model is to have a holdout set, so a data set that the model never saw, containing also images from the same labels, but they are different from one we trained on. And then we're gonna test it on these images and see how the model is classifying these images and how good it is performing on this. Is everything clear until now? Okay. So I've talked about probabilities. So what we want is that from this image, get probabilities of each class. And now the question is, how can we get these probabilities? So in most cases, what will happen is that this function f will just output some number, the scores, some scores, which can be positive, negative, and so on. And then after, we're going to apply this softmax function onto these values to get probabilities. So the question is, how do we get probabilities from scores? So the objective is that for probability, as you may know, the probability must be between 0 and 1, and the sum of all the probabilities must be 1. And so that's what we want for probabilities. And what we have for scores is that they can have any values, and they also do not sum to 1. So these values could be arbitrarily big or small. And the only thing we know is that the bigger it is, the more likely the category is according to the classifier. And the smaller it is, the less likely it is. So how can we do that? So one solution could be to define some kind of normalization factor S, which is the sum of all the scores, and divide each score by this normalization factor. So this allows to have something between, well, in this case, minus 1 and 1, because we have negative values, so this will be negative. And also, this assures that if we sum everything, it is 1. That is thanks to the definition of the normalization factor. So if we sum everything, we just have S over S, and so we have 1. But yeah, this problem is that these values are not necessarily positive, they can be negative. And this normalization factor can also be 0 if all the scores are 0. And in that case, we have a problem because we divide by 0. So a solution to this, so this is almost correct solution, but the solution is to use the exponential here instead of directly, so the exponential of y instead of y in that case. And that allows for, because, well, so exponential is strictly increasing, so we don't change any of the thing we want here. And also it's strictly positive, so we would not have this equal to 0 anymore. This wouldn't be possible. And also, if we had negative values, they would become positive. So everything is positive, strictly positive, and this is a problem. And so this is the definition of the softmax. Okay. this is exactly this. So for each score, which would be xi, we define the probability or the softmax of the score here to be the exponential of this score dividing by the sums of the exponential. Okay, is this clear? Okay, so now we've seen how to go from scores to probabilities. The question is, how do we learn the function? So how do we find a good function that can go from an image to the correct label? So of course, if we get a random function, we are not assured that, I mean, it could give for a cat, it could give a car because, I mean, it's random. So it could give any values. And what we're interested in is a good function, which is a function that takes an image of a cat and says it's a cat, and when it's a dog, it says it's a dog. So like you've seen that probably in the previous lecture, but what is learning a bit kind of a recap. So we have a set of functions, we have lots of functions, F1, F2, they do different stuff. And among all of them, we have the best function, F star, which is the one that we want, which is the one that classifies the best among all of the functions. And so the goal is to find that function among this set of functions according to some criterion. And the criterion is, so we have this, what we said before, this test set, this set that we, a data set that we didn't train on with a lot of images and labels that we can test our model on. So, and this is going to be our criterion. So at the end of training, we can evaluate how the function predicts for each image, the class, and compare that to the actual class. And the better the results are, the better the function is. And we can so find the best function like this. But actually finding a good function from a certain function is very hard because a certain function is very large, and in practice, the way we solve this is by parameterizing, meaning that we're going to have just one type of function, but that depends on input, of course, but also some kind of parameters, W, which could be a matrix, for instance. And now we just have to find the best parameter. So the W star would be the parameter which makes this original function best suited for our task. And this is easier because I mean, we know it's easier in terms of linear algebra, how to find optimum matrices. We know how to do that. However, finding best function is very hard.
So here we're just using one function and varying the parameters.
Exactly. And what the function is actually is a neural network. So the function in itself here will be a neural network. So what you saw last week is kind of deep layered rows of neurons that go from one to the other. And the weights, so the parameters of this function will be the synaptic weights between each neuron. So how the strength of the connection between each neuron. Okay. And so now let's take this example with this. Let's say that this image is 32 pixel by 32 pixel, and also time 3. You remember we have images RGB values, so we have this time 3 here that happens, and we need to go from this to the scores. And so what happens is we take this image and we kind of flatten it. So if you see that you have a 32 by 32 by 3, actually you could also say it's just one large 3072 vector. And so because we have a vector, we can use the MLP structure that you saw last time and just apply the different layers and get outputs here. And the output here would exactly be like the values of the scores of the function. And then you would use a score function. So you would learn this with your targets. So let's say that you know that this is a cat because you have data set with images and labels. So you know that this is a cat. And so what you can do is to have cat to be the highest and the other one to be very low. And so here we find what I was talking before on how to train it. We have F, which is our neural network that never changes. X, which is our input. So this is this image that is flattened into this big vector. And our parameters are the synaptic weights of or the weights of the neural network. So we can look at if we have only one layer of if we have a one layer neural network. So I don't know if you remember this one layer or this equation from last week, but a one layer neural network, you define the output as W times X. So X the input, W would be your weight. So for instance, here you can have a weight that go from 3072 neurons to 10 neurons. And then some potential additional bias, which is a vector that you would add at the end of the computation. And so from this 3072 vector, after this one layer pass, you would get a 10-dimensional vector, which is way smaller representation. And if you had, let's say, 10 classes, this could correspond to the scores of classification for your model, and you would have a one layer classification function. Yes. From when? Yes. So here we're doing a matrix multiplication. Do you know how to do matrix multiplications? Okay. So okay. So I'm not going to go in details about how matrix multiplication works. But what's important here is that it's the size. So here, if you have do you know what matrices are? Or should yeah, okay. So if I have a vector of size, so 3072 times 1 here, and my matrix here is of size 10 times 72. So the dimension of this one and the dimension of this one must match. Okay, it must be the same. And the output, so the output of this product will be of size 10, so the one that stays on the left here, times the one that is on the right here, okay? So the output of this would be, so this will basically collapse, and you will end up with something that is 10 times 1. And that's why 10 times 1. And addition for matrices is just adding row by row. So if you have two tables, two matrices, you add for each row the same. So if we have something here which is 10 times 2 on dimension, we need something which is also 10 times 2 in dimension here, so we can add the two together. All right. Maybe if we have time, we can look later about like what matrix multiplication is. But yeah, the whole thing here is that we are multiplying. Do you know what a dot product is, or produit scalaire? No. Okay. Okay. Is that clear, or does okay? So yeah, this is just a recap. This is the function we just saw. So W are the weights, B is the bias, X is the input, so the image, and then the output. So the result of the function would be the class scores. And yeah, it's just a recap here for dimensions. We already saw that. And now we'll talk a bit about the interpretation of this. So we've seen the computation and the equations, but what do they mean? So you could see this. One way of seeing this is template matching. So in one layer, you wouldn't have a good accuracy because it's very difficult to represent one object only with one tensor. So here it's an example with one tensor. Here it represents W as an image. And so what you're trying to do basically is match some kind of image with another one. And so the one that is the closest or that looks the most similar will be the one with the highest score. And so for each of these, you can see that it's kind of a blurred version of an average, like an average cat or like blurred. I mean, you have to squint very hard to find a cat in this image, but with one layer, you don't expect to have very good performance. So this is one way of seeing this. Another way, which is a geometric interpretation, is to find boundaries. So imagine that in this high-level space, you have lots of images which are located in this space. And what you're trying to find is a line that separates one class from the others. So for instance, this line here separates all of the images that looks like planes from everything else. Same, this one, so you have lots of cars here. This one tries to find the boundary, like to split into the space where you have in one direction the cars and one direction not the cars. And of course, with only a linear thing, you can only have linear. So this is why it's very hard, is because this is linear, you can only have linear lines. And so you will have many mistakes because probably the shape, the space is not linear, and you could have, like for instance, this one is also a car and is missed by this classifier because, I mean, this was the best compromise. If it also included this, it would have included some chicken underneath, and it's not good. So yeah, so you have to have a compromise, and so therefore you cannot have a very good performing classifier. And so, of course, the solution to this is to have multiple layers. So you've seen last week, I think, the MLP, so the multi-layer perceptron, how to go from this linear one to the two layers. So we would typically add a nonlinear function here, like like a sigmoid, and then do the same again. So have another W and another B, and then multiply this output, which has been through this sigmoid function with a W2, and add this to a B2, and have the output at the second layer. And you could do that for how many layers you want. And yeah, the fact that you have the nonlinearity function, so the sigmoid, then this becomes nonlinear. And so you could have, instead of having straight lines here, you could now separate the space with something that is curved, for instance, and have more precision. So yeah, so like this is a kind of a recap slide where we've seen the algebraic or the equation side of things, a little bit of a visual side with this template thing, or like trying to find the one that is closest. And then this last one, which is geometric, so like finding these lines that separate the space. And so this is a very simple way of doing classification, and it works if you have small images and not very diverse. But Now we're going to talk about convolutions and why they allow us to have better performing models on images, and actually not only on images, on pretty much everything. Okay, have you ever heard about a convolution before, or of the term convolution? Okay, so it's probably the same. I mean, it is the same, and we'll talk about like in details what it is and how to do it. So yeah, let's talk about this convolution layer, this convolution thing. So here we have a representation of our image. So like a 32 by 32 image, height and width, and remember these three-dimensional RGB values, red, green, and blue. That's still there. And we want to go from this. We have this image, and what we will do is to have a filter. So here it's a small 5 by 5 by 3 filter. And a convolution will apply this filter to the whole part of like each part of the image. And so to do that, we introduce the sliding window principle. So you have to see it from the bottom up. So like at the bottom here, you have an image. The black square that's sliding here is the filter. So it's a 3 by 3 filter because so each block here is 1 pixel, let's say. And so this is spanning 3 by 3. And you see that for each 3 by 3, you get every time one value. Okay, so it takes the 3 by 3 part of the image that's interested in its weights, because it has weights, and from this we'll compute one value, and then once it is done, you slide it one to the right and you redo the same thing. And so from this big image you can have now an output which is a bit smaller, because you remove basically one from each side, one dimension from each side, which has been computed with this sliding window principle.
The filter has a depth of 1. It's not
Not necessarily. You can have any depths. So here it was the most typical sliding window, but you could also imagine that instead of shifting by 1, you shift by 2 every time. So in the in both directions. And this is what we call stride. And finally, so here, every time we do this, you see that we lose some pixels on around. And sometimes you actually want to have the output which is the same as the input. And so to do that, you can add padding, so add some random values. So like the values you put around could be either a fixed number like 0, or like copying the closest pixel. So like so if you put 0, it's like adding like this kind of black border around your image. But you could also imagine, yeah, extending your image, so like copying the pixel that is the closest here, and you would have just like one more layer around. And so we're basically increasing the input size, so you would have the same output. And that's called padding. So what you add on the input image. Okay, so let's go back to the convolution layers, and maybe we can look at this website. No, this one.
Increasing the movement of the filter to capture the image.
No, you don't increase the movement. You add on the input. You increase the size of the input basically. And so you still have you still shift your window by 1. But in like the first one will have these additional padded values. And so you could basically, instead of starting at the very top left here, you start 1 to the left and top, so that you get the same output. dimension as the input. I mean, here it's padded by 1. You could also imagine padding by 2, or I mean, if you have a bigger, because this is a 3x3 kernel, if you have 5x5, it would be, you would need even more padding on the side to have the same dimensions, but yeah, same principle. Okay, so let's look at this block because it's quite interesting. So here you have an image, and on the right you can see, okay, it's very small, but it's numbers basically, which correspond to the gray. So here it's not color, so we don't have RGB, we just have gray, the gray light luminance. And you have this value on the left. And so we'll talk about filters. So here, the filters we have are just one-dimensional. So you were asking a question, can there be more than one? So here we restrict ourselves to the one-dimensional. So, and then we'll go further, but to start with. And so here we have a 3x3 filter. For instance, this filter, let's even get I want an easy one. Yeah, like this one. And so here on the left, you can see like the input image, and on the right, you can see like what it does to the image. So the output after the filter has been evaluated the same way I showed with the sliding window. So here, bottom subble will kind of highlight horizontal lines. So you see like here you have kind of a horizontal, like the white part here is this horizontal part in the hair. Here you see you have some kind of horizontalness and the eyes as well. So this is bottom subble. You could have also something right subble which would highlight vertical lines. So here you have more like verticality that appears. Or you could have like more evolved like blurring, for instance, that would just blur the image, or sharpen, which basically looks for edges. So it's kind of a combination of the vertical and horizontal lines, but it just sharpens all the edges. Okay, and so now we look at how we compute that, how the output is computed from the from this kernel. So this is called a kernel, by the way, the kernel of the convolution. Okay, so here we have in red on the left, we have this sliding window, and you see on the right that we have only one values. So for the 3x3 that we have on the left, we get the output is this one value on the right. Okay. So you see that also they have padding. So that's why you have this black border around to get the same value. But if we go on the very top left here, we get this white pixel on the right. And so the way it's computed is the computation that is on the bracket in the middle between the two images. The values in the big squares are the values of the image. So not the RGB here, the gray values. So also you can see directly the luminance, and it corresponds exactly to what we see on the 3x3 square on the left, on top left. And then under that, you have times and a number for each square, and it corresponds to the values of the filter. So here the filter is 1, 0, -1, and so you have it here, these coefficients 1, 0, -1, 2, 0, -2, 2, 0, -2, and so on, okay? And so the way you compute for each window is that you take the pixels, the pixel value, and you multiply each pixel by the coefficient of the filter, and then you sum all of them together. And you get this one value on the left, on the right. Is that clear? Once you've done that for one, you shift by one, and you can compute that for every 3x3 section in the original image. and you get this output here, this output here. And so here I show you some predefined filters. So you could look at different filters. But in practice, you want to learn those filters. That's because we're doing machine learning. So there's something we have to learn. We said before that the function f is always the same, but we just change the parameters or learn the parameters. Here, what are the parameters? Well, they are these filter values. So the parameters of the filter here, that's what you're going to learn. So you're going to have some random values at the beginning, and you're going to multiply your input to this, get an output, and then you're going to try to find the best filter that optimizes your task. So image classification. Okay. Is this clear for this convolution, like this convolution operation? Let's go back. So again, you have your filter. So here you see it's a 5 by 5 by 3 because well, you have, because you want to have you need a 3 here because you have a 3 depths in the image, right? So because you have, so before we had just RGB, which is 1 value. Actually here, sorry, we had grayscale, which is 1 value. Now we have RGB, which is 3 values. So you need to apply the same thing for the 3. And at the end, you sum everything, okay? It's the same principle. You multiply basically each of the values with each of the values here and sum everything, and you get one number. So is it clear how you go from this 5 by 5 filter? We saw like 5 by 5 by 1, and now we go back to 3. Okay. And so from this, so you do the convolution on the whole image with this sliding window, and you get so this one, which is a bit smaller because we removed the 2 edges, and you get what's called an activation map. So this is what we call an activation map. And from this, same as this, very similar to what you would do with multi-layer perceptron, you could have on this, you could apply a sigmoid function, for instance, or a nonlinearity function, and then do the same again with another layer of filters. Actually, a filter, because here we've seen with 1 filter. But what you could want is actually to have 2 activation maps. And to have a second activation map on the same image, you would take another filter. So you had 1 filter for this one, you take another filter, apply the same on the image, and get the second activation map. And actually, you could have many filters. And so, for instance, here we could have 6 5 by 5 by 3 filters, and you would have 6 activation maps. And so, but by the number of filters you apply on your input image, you would go from, so this 32 by 32 by 3 into a 28 by 28 because we have 5 by 5 filters. So we reduce this by the output dimension by 6, which is the number of filters you applied to this. And so you can control basically any dimension. So in depth by the number of filters, and in height and width by the size of your filters. Okay, so going from this to this, we extract information, or we extract features, but we reduce. So don't forget that at the end, our goal is to do a classification. So for classification, we need 1 number, or we need like an array of number which correspond to the different classes and predict probabilities. But this is way too big, right? And we need a way to reduce the size of our maps. Otherwise, we won't have the right answer at the end. So we need a way to reduce dimensionality. And this is what pooling layers do. And so pooling is basically having this 224 by 224, so this height and width, times 64, which is the number of filters of the previous operation, into a smaller version of the image. So same number of filters, but smaller image. And so to do that, we just downsample. So what is downsampling is just, so if you imagine your image, your original image here, you can split that into several quadrants. So for instance, 2 by 2 squares. So here you could have like 4 of them. And for each small square, you keep only the highest value. And so here you divided by 2 your size of your image by just keeping the highest value in each quadrant. By doing a max pooling of size 2. Okay, so that was for this. So how do you go at the end into this vector of scores? So the goal is to have the different scores to be the length here of the depth here of the output. So if you have like a classification over 3 objects like cat, dog, and car, the output here should be 3 at the end. And then the goal is to have this reduced to a 1 by 1 pixel, basically, by 3. And this would be your target vector, your prediction of score. Okay, now we're going to talk about receptive fields. So what is a receptive field? The receptive field is basically the area in the image, in the input image, that each neuron has access to, can see, basically. So if we imagine here that this is the different values of the input image, of the input, which are connected like this to the second one. If we ask what is the receptive field of this neuron, it is these 3, because it's the 3 neurons that this neuron has can see. So similarly, if we ask what's the receptive field of this neuron on the bottom, so we have to look at what this neuron can see, and it's this one, and this one. Finally, if we look at the receptive field of this last neuron, so we have to look at the receptive field compared to the first layer. In that case, it's, well, the 2 intermediary neurons. And then we have to also ask what is the receptive field of each of these. So for this one is D3, for this one is D3. And so the receptive field of this neuron is all of these neurons, or all of these values. So it's basically, when you look at one neuron in the architecture, what does it have access to? What can it see? What can it see? Okay, now in terms of convolution, it's exactly the same. So if you have an input, a big input like this, remember each 3 by 3 gives 1 value. But if we look at this 3 by 3 window, we will get this one here. And so if we ask what is the receptive field of this value here, it will be this 3 by 3 grid from the input. Okay. And now if we combine 2 convolution in a row, so we do a convolution on the input, we get this. Now we do another convolution on this map, we get this. So what is the receptive field of this neuron? So as you know, like a receptive field of one neuron is a 3 by 3 grid. So we get this. And now we have to ask basically what each of these values, what the receptive field of each of these values are on the input. So that was the first step. And now what is the exactly. So you would, from each of these values, you would see like on this one what it corresponds to. So this one is D3, then the second one, and so on. And so your region would be 5 by 5 here and corresponding to, so these neurons here has access to this 5 by 5 region of the input. So this is this demonstration is just to tell you that if we have a one layer network with filters, each value will have a context basically of only 3 by 3 if you have a 3 by 3 filters. But if you change then in depth, so if you have a second layer, which also is a convolution on the previous layer, then you can still have a 3 by 3 map, a 3 by 3 filter, which is very small, but has access to information on a way larger region from the input because of this chain of windows. It's good, it's good. It allows to have a bigger context. So if you have only a 3 by 3 image, so I don't have this here, but imagine this image of a cat. If you look just at a 3 by 3 pixel on the top, it's very difficult to classify this as a cat because it's only something dark, something light, you don't really know. But if you have access to bigger area from the image, then it becomes easier because, okay, now you see there is actually eyes and nose and whiskers and whatever, and this is easier to classify. And why is it better to do this rather than having a very large filter? Because if you have a very large filter, let's say a 15 by 15 pixel filter, you can also do that. You also have a lot of context. The problem with a 15 by 15 layer is that you have 15 by 15 weights inside, which is very large. And if you, instead of that, had a combination of small layers, you would add small values, and so you would have less weight in the end. So less weights to learn than if you had a very big filter. And so it's better for, so it's easier to compute, easier to train, and yeah, and it takes less space as well because it's smaller. Okay, so we're gonna skip this. Yeah, also like the presence of a max pooling will affect also the receptive field because, as you remember, like max pooling is divides your input by 2, so you increase your receptive field by 2. Okay. Now I'm going to talk very briefly about visual transformers. I'm not going to go into details about what a transformer is. You're gonna have a lecture for that later on, but it's going to be focused on text. And here I just want to give you some context on how to apply this for visual. So I'm going to try to make it very easy. And if you don't understand, once you've seen transformers with text, you will go back to the presentation and maybe understand a bit more what I'm saying here. But I'm going to try to make it easy to understand. So let's imagine that transformers here is a model. So a bit like the perceptron that takes, instead of having one input, which is one vector, it takes a sequence of vectors. So each xi here is a vector, and it can take an arbitrarily long amount, an arbitrary number of tokens. So we call them tokens, but it's of vectors. It does some computation, and it outputs a sequence as well. So the output of the transformer is also a similar sequence from the input. So why is this relevant for image? Well, how can we see an image as a sequence? One idea is just to split the image into smaller images. So for instance, here you could split your image into 6 sub-images. And so if you have a very large image, then you would want to split it so that each sub-image is smaller. Let's say like 10 by 10 or 16 by 16 image. And so each of these part of the image is in itself a vector, because you remember we can just flatten each of the values and get a big vector. And so now you can transform your image into this kind of sequence of images and give that as an input to a transformer. And I think, yeah, I think it's all I give you. I'm sorry. It's very abstract and you don't have a lot of information about what the transformer is, but you're going to have a lecture on that. And I'm just giving you how you can apply these two images. And the way you do that is by splitting your image into smaller images, which are your tokens. Okay, and why transformers are interesting? You might have heard of ChatGPT and all of these large language models. This is basically the architecture, a transformer. And until, I mean, at the beginning, it would handle text. Now they're multimodal. They can handle images and whatever, and audio and whatever you want. And this is how they compute, or this is how they process information or visual information by splitting an image into smaller images and having this as a sequence. Okay, again, you'll see that later. Okay, now let's finish up. We're gonna look at some data sets that are very common in the literature. So you have different kind of tasks. I've talked about semantic segmentation at the very beginning, or object detection, or image generation would be to generate images. So you know, like all of these DALL-E and Stable Diffusion, whatever, like this is image generation. Image denoising is when you have a very bad image and you want to have a sharp image or remove noise from the image. This would be image denoising. Here we focus on image classification, which is what we saw. So some classic data sets are MNIST. So this is digit recognition. Another one is CIFAR, which is like 10 classes of small images. So these are very, very easy data sets that we'll talk about. Actually, the practical session will be on CIFAR. Then you have real high resolution images, ImageNet, which contains a lot of images, and in particular, the particular data set that everyone uses is from a challenge and is a subset of ImageNet, which has 1,000 classes, so 1,000 categories of objects you could have in the image. Yeah, and big image, like the image are this size. Yeah, okay. And in terms of models, yeah, we can skip this. So yeah, okay. Well, okay. One of the first model, like known visual model that exists as the neocognitron, which combines supervised and unsupervised learning. Then, yeah, you can use it, for instance, for object recognition, text recognition, or character recognition, like OCR. And then here are some kind of like the trend or the different models that appear on this timeline. So AlexNet is first winning entry for the ImageNet dataset. Then VGG, which, okay, we're gonna go, I think, yeah, we're gonna go into detail. So AlexNet started to go bigger, leverage multiple GPUs. So like these graphical cards for faster compute and very deep, so like 8 layers deep. 60 million parameters. So these filters that we talked about, 60 million of these values that you have to train. And it was layered in that shape. Then GoogleNet, which introduces this kind of inception network, which is a kind of a hybrid network which has different kind of paths. So like from a previous layer, you can have either 1x1 convolution or these 1x1 and 3x3 or whatever, and then they all combine. And so it's kind of a way to like pick and choose depending on your model, and a very deep model. And it's so deep that it's very, at the time, it was so hard to train that you couldn't train it end to end. So like have your whole models, give your data and have it trained. No, you had to have this kind of heads, intermediary heads here, that you would train only this section of the model first. Then once this is trained, train with this section here, and then gradually do it over the whole thing. I mean, and then VGG is also is the next thing that was very, very deep. So I did a lot of layers, 19 layers in total, and 140 million parameters. Also, like at the beginning, they had to train it in a similar fashion with in steps. So wait, the details. And then came ResNet. So ResNet is also very deep. And what they did is that they added this kind of skip connection. So if you have your input here, your weights, so your computation, so your convolution you would do here. And then you could also choose to not do the computation and skip it and just have this value here. And so this trick allows for better gradient flow, which means that it's easier to train. And starting from this network, it became, I mean, a standard. And it allows to not have this kind of trick where you have to train your model sequentially, and you could do it like end to end, because you have this gradient skip connection that allows for a better flow of gradient. Yeah, also very deep. You can see that the number of layers here increases. I mean, here you had a very low number of layers, already VGG 19 layers, GoogleNet 22 layers, and ResNet 152 layers, and you could learn it directly. And of course, these are the blue bars are the accuracy or the error on ImageNet, and you see that the error goes down with, well, number of layers, but also like years, basically. Okay. I suggest we take a break. I don't know, like how long do you want? Like 10, 15 minutes? Is that okay? Okay, so we'll take a break, a 15-minute break. If you have questions, I can answer them. And in 15 minutes, we'll go to the practical session. Online, if you have any questions, also you can, I see there is nothing in chat or, I don't, yeah, if you have questions, don't hesitate, I will answer them. This is not public? C'est pas, vous n'avez pas accès à ce truc-là? Non? No. All right. Anyone? Yeah. B. Ça devrait être bon. C'est bon? C'est pris d'où? Bah, sur le site maintenant, là? Non, c'est bon, on fait la demande. Non,
Il est revenu aujourd'hui. Et moi, c'est-à-dire, que moi, je trouvais que c'est là qui m'a de la gueule, il m'aurait fait dépasser comme tu m'avais dit, et tu m'as dit que ça va être il m'arrive. Après, il y a des côtés avec c'est juste, mais on est passé en moins de 3 j'ai l'impression que j'ai juste assez publié, et puis je vais faire un papier, après, je te trouve, parce que je serai pas aussi bien fait que je suis pas bien. Bon. Ouais, je trouve que ça rentre bien dans le truc. C'est faire avant 5 minutes, mais dans rien de 5 minutes. C'est très un peu plus bon. Je suis pas plus bon pour le truc. En vidéo? C'est chaud quand même. Ça, j'ai pas de non, c'est bien. Oh voilà. J'aime pas l'espagnol. Et c'est que, en plus, il était dit, dans un bateau, ça parle. Voilà, après, elle a dit ça. Je l'avais envoyé à Amélie, elle m'avait dit que j'avais envoyé les chantiers, elle avait dit que elle avait dit pour elle faire. Et là, c'est pas elle qui était absente, c'est là, le changement. Non,
We all here? The hour with a practical session. Normally you have the link in the presentation, yeah. In the presentation or on the website. So on the website, lecture 2. Here, the tutorial notebook. And you need to have a Google account, Google Drive account to access this. And then when you have it, probably you can, if you want to copy or change things, you can probably copy the file or something to your own drive, Google Drive. Okay. So this, the goal of this notebook is to apply a convolution model on MNIST, so the MNIST dataset, which is the dataset I'm going to show you. Yeah, this one, the hand digit recognition dataset, so these digits. And so, okay. We're going to use a library which is called Torch, PyTorch. And this library is handles all of the neural networks, all of the automatic differentiation, all the calculus, all the equations that you have to solve and so on to and the optimization process that you have to do to find your best parameters. And yeah. And also we use Torch Vision, which is a library based on Torch for vision. So for the notebook, you have text, but you also have code, and you can execute the code by clicking this play button here, run cell, and it's going to basically it's like you have a script, but everything you do here will be kept as a memory, and you can run following. So here we see that we have PyTorch 2.1. And first thing we need to do is to load data. So here, this one here loads data from these websites. And then defines a data loader or a dataset here, a try dataset, which contain the images that we downloaded from the website and the labels. So you also see this, like this batch size parameter. Have you heard about batch size in the previous lecture, or doesn't ring a bell at all? So yes, I can. Okay, let's give a recap then. When you want to train your model, you train this on images. And usually, instead of looking at one image at a time, you look at the batch of image. And this is the number of examples that you're going to look at the same time. So like every time we're going to do a pass, we're going to have a batch of 32 images. Okay, now a bit of exploration. We have this imShow function that can show an image. We're going to take one batch from our data loader. So because we said 32, we're going to have 32 images and plot them here. Yep, I thought I changed that, but apparently my changes didn't work. So okay, if you copied here, it was like dot next. You need this next. I'm pretty sure I changed it, but anyway. So did you all see the change that you had to do? I mean, I'm changing it on the original one. So if you look at it later, you have the proper version. And so here we're looking at some examples, some of the images that we have. So the handwritten digits, there is a lot of variety. So for instance, different 8s that looks very dissimilar, or 9s here, you see that you have a lot of variation in the 9 here, or here, or here. And we're going to have to do some classification. So classification here will be we're going to have an image of 1 digit, and we have to say the number or the digit it corresponds to. So here 8, here 3, or here 0, okay? So that would be one exercise for potentially if you take this for your evaluation, you could give an explanation about a detailed explanation of what this is doing. So Now we're going to take one image from the train loader, one batch of image, and we're going to look at its shape. And we see that the shape dimensions are 32, which is the batch size, times 1, because these are black and white, so grayscale. And then 28 by 28 are dimension of your image, so height and width. And then the labels are the classes. So here you see that it's just 32. If we look at it, we just print the labels. You'll see that it's just an array of numbers. And if you have 4, that means it's an image that looks like a 4. And if you have 0, it means it's an image that looks like a 0. Okay. Okay, now let's define our model. So the model, again, it's the function that computes the scores from the image. And in PyTorch, you can use, have you done some Python before, or is that, okay, so do you know about classes? Okay, do you know about inheritance? Is it only you or is it everyone? Not you? Okay. So a class is kind of like an object, so something that will encapsulate or will group together different functions and a state. The state is defined here in the init. So the init is called whenever you create a new instance. We say a new instance is when you make a new object of my model. You will define the state here. Okay, so here in that case, so every time self references the object itself. Okay, so here we define a new variable in the object. So in self.conv1 says that the variable conv1 is in the object. And we define a new convolution layer. So NN references the torch library. And conv2d is a 2D convolution, so exactly what we saw in the lectures before. In channels correspond to the number of channels in the input. So in the example we had in the lecture, it was 3 because of RGB. Here it's grayscale, so it's 1. Out channels will be the number of output. So the number of filters that we're going to have inside of our convolution layer. And kernel size is the size of filter. So E3 means 3 by 3. And then we're actually going to compose that with two linear layers. So we're going to have one convolution, do the convolution, get a new map, a new activation map, and then transform that as you would transform an image into a vector, because this is basically a vector. You would flatten it and then pass this in linear layers. So it's exactly like a perceptron, is WX type plus B. And so linear needs input dimension. So here, to get the input dimension, we have 28 by 28 times 1 images. We apply a 3 by 3 filters. So we're going to remove some values on the surrounding, and we get a 26 by 26 by 32 because we use 32 filters. Okay. And so this would be our input dimension for our linear layer. And the output dimension here is just, we decide to have a 128 dimensional output. So if we apply D1, we'll get a vector of size 128. And then we define a new linear layer, which goes from a 128, because it's the output of the previous layer, into 10. Why 10? because we want to classify digits, and there are 10 digits. So it's the number of classes. So this is the state of our model. So it initialized when we initialize. And we define here a method, so a function that is associated to the instance of the object. So we can access to self, which is the state, and have another parameter, x, which will be the image, the batch of image. So batch of image means there is 32 images. One, again, it's the grayscale values, and 28 by 28 is the size. So we can apply the convolution. Convolution goes from 1 by 28 by 28 to 32 by 26 by 26. And we still keep the batch size at the beginning. The batch size doesn't change. 32 is this 32 here. And then 26 by 26 would be this. So this is effectively what the convolution does. Then we can apply a nonlinearity function. Here we apply a ReLU function. I probably should have showed you this, but we can look at it online quickly. ReLU function. It's just a step. It's just a linear function when it's zero above zero. Okay, it's always zero in the negative values, and then it's the identity on the positive values. All right. And then at the end we flatten everything except from the batch size. The batch size we want to keep, but the rest we flatten into a vector. And then we can apply our first layer, then our nonlinearity function, which is a ReLU. And then we apply our second layer, and we get what it calls logits, which is what I call scores in the lecture. So and then our softmax function to get probabilities. So softmax, remember, is the exponential divided by the sum of exponentials. And then we return this output. And so that's our class, that's our model. One convolution layer, two linear layers. So here we can test the model with only one batch. So we're going to do a for loop over the data loader. Look at the batch size, or look at the size of the images. Execute our model. So here, see, this is how we instantiate a new model. So model, this is what we define here, right? And the parentheses would be what we would, if we had parameters here, we would need to give it here when we instantiate the model. Oh, where am I? And then we get an object, an instance of my model. And so we can execute this. So you don't, I mean, it's not shown here what executes this. It's in this NN module. It's defined by the parent class, but basically it will do the same as forward. Okay, it will apply the forward function. So when you do this, it applies forward, and you give it images, and the output would be this out. So this softmax logits, and we can look at the shape of this. Okay, so just to test, we execute one, and then we break. Break means we stop the for loop. We just do one iteration. So we see that the image is 32 by 1 by 28 by 28, like before. And the output is 32, so batch, because we have 32 images, times 10. So for each image, we have the probabilities for each. We can actually maybe look at just one. So if we look at out 0, so the brackets here, it says we look at the first item. So from the 32, we only look at one. And so here you see what it looks like, and these are probabilities. So there is 10% of the first one, and what you see is that everything is around 10%. But this is normal because our model is randomly initialized, so we shouldn't expect the model to know, like, to classify from random initialization. And we should have random attribution of probabilities, and that's what we see, right? Everything is approximately the same probabilities, which is 1/10 because 10 classes. Okay. Now we go into the training of the model. So we're using what's called gradient descent for, I don't know, have you seen gradient descent in the previous lecture? Have you talked about, does it ring a bell, or backpropagation?
Yes.
Okay, so this is the algorithm we use to train the model. And we need a learning rate and number of epochs. An epoch is, you do one epoch when you've seen the whole data set once. If you do a second epoch, that means you've learned on one time the data set, and you start over a second time with the same data set. So here we say we're going to look at 5 times the same data set. Device is just, we say to the model, we're going to use a GPU if it's available. On this website, on Colab, you can actually use GPUs to train your model. So if it's available, we use GPU, otherwise we use CPU. But here we have a GPU accessible, so we use a GPU. We instantiate a new model. We put that model on device, so we put all the memory on the GPU if it's a GPU. And then we define our criterion, so our loss function, which is here a cross entropy. When you do classification, you usually use the cross entropy loss. The goal of cross entropy is basically, when you have your scores here, to have highest score for the one that is correct and lowest score for the other ones. Okay? And then your optimizer is how you update your weights. And so you can have stochastic gradient descent. Here we're using the Adam optimizer, which is nowadays one of the most common used because it's very fast to train your model and very efficient. And so what it takes is the model of parameters returns all the parameters of your model, so all the weights. So the filters, the linear layer weights, the biases, everything. So it takes this as a parameter, and also the learning rate, which is defined before here. So we can run this. So this is just defining variables. It doesn't do any computation. Then we define new function, which is called get accuracy, which takes the logic, so the scores, the target. So the target is the class number, like 0, 1 to 10, and the batch size, and computes accuracy. So how do you compute accuracy? Well, if you have scores, to get the one that is selected, you have to get the maximum. Okay, so .max will get the maximum, the index of the maximum value. And then you check basically that it's equal to the target. So if you get, if the 5th one is the highest, that means that it predicts that the class is the 5th one. And so it should be the same as the value in target, which is 5. And so if it's correct, it will be 1. If it's not correct, it will be 0. And so we sum everything, and we basically have the number of correct predictions. Okay? And the accuracy is the correct number of correct prediction divided by batch size, because we have 32 examples. So maximum value is you have 32 correct. We want to normalize that over probability, so we divide this by 32 and multiply by 100 to have something between 0 and 100. Okay? You know what? I think this is very poorly written. And it should work. and it's easier to read. Okay, so it does exactly the same. It's just instead of this weird text, let's use the argmax function. Argmax gives the location of the max. So if you have 3 values, if the third one is the highest, it returns 3. If the second one is the highest value, it returns 2. It returns the rank of the highest value. Okay, now we can train. So we do several epochs. So we do a for loop over the number of epochs. We're going to track the running loss, the loss function, and we're going to track the accuracy. We need to put a model in train mode. So we do that. Then we iterate over the train dataset or the train loader, so all of the batches basically. And each step we're gonna have one batch of images and one batch of label. We put those into the device, so either the GPU or the CPU. Here the GPU. We evaluate our model, so we get the logits from or the scores from the images. We get the loss by evaluating with the criterion. So remember, criterion is this cross entropy loss, which basically tells it's going to be a high loss, so very bad, if the highest score is given to the wrong label, and it's going to be very low, so low loss, low error, when the correct label has the highest score. And so you need to give the scores and you need to give the label, so the correct ones, the one that you have, the ground truth. Then you need to remove all gradients already present in the optimizer. Loss.backwards computes all the gradients. And then you can do an optimization step. So this will update all the weights in your model. And after that, you should have a slightly better model. But of course, you need to do that over and over again over all of your datasets and several times over all of your epochs. Then we're going to add the value we're going to keep track of the value of the loss and keep track of the accuracy. And at the end, we're going to print at the end of one pass over the whole data set, we're going to print the average loss and the average accuracy. Okay, let's go. So now this starts to compute. We can see the marker here where it's doing things, where it's at. I mean, this is very slowed down because it's actually going way faster than we can see it. Okay, so here you see that after one epoch, we have an average loss of 1 and an accuracy of 84%. So 84% of the images in a data set are not correctly labeled with our model. After a second epoch, we see that it improved. And again, with the third epoch. So we're going to let it train, let it finish. So as you can see, the improvement is non-linear. It improves a lot at the beginning, and then it fine-tunes a little bit, so it gets a little bit better, but not necessarily much. So this is most of the time is going to be a similar trend. So it learns a lot at the beginning, and then you need a very long time to get it to the best value. Okay, so now this is the value on training set, right? So this is what the accuracy we get on the examples that we trained our model on. But we don't really know if the model learned a general rule to classify those images, or if it just learned by heart. For instance, it could learn by heart every image and say, okay, I know that I've seen this image before, I know it's a 7, and so give 7. But this is not what we want, right? We want to recognize digits. And if we just learn this example by heart, then we won't be able to, it wouldn't work on new examples. So to test our model, we're going to use a new set, which is a test loader. Is it defined? Did we define it? Yes, here. We also defined here before the test data set, which we use now. And so we haven't trained the model on this, and we're just going to evaluate. So do the same, go over the whole images, keep track of their accuracy, evaluate a model, and actually put the model in eval mode. This was missing. And look at get the accuracy and see how good the model performs on new data. And so we see that the model performs, so can accurately predict the class on 98% of the images. So it's approximately the same here. So we can conclude that the model learned a good strategy to classify the images, and it's not just learning by heart the examples. Yeah, so that's basically the tutorial on MNIST. So about applying what we've learned on some examples. So here the digits. Here you have some going further things that you can practice on. And yeah, that's it. If you have any questions. Is that clear, or other things that are unclear, or that needs to be clarified? So, okay. Ok. On passe en français. De façon globale, est-ce qu'il y a des choses qui ont été pas claires dans la présentation ou dans le... Enfin, il y a des choses qu'il faudrait plus peut-être détailler ou... Ok. C'était plus difficile la semaine dernière ou pareil? Ouais.
C'est là, par exemple, c'est la position de la témoignage, c'est pas des liens inconnus, le fait d'avoir des images aussi, je pense que c'est plus parlant que ce qu'on a vu. La semaine dernière, on parlait juste de moyens et je sais pas ce que c'était.
Ok. Et ouais, peut-être aussi... ouais, j'ai peut-être pas fait beaucoup, mais faire des parallèles avec ce que vous faites de la cancérologie, c'est ça? Comment? Ok. Donc, peut-être faire des parallèles, pourquoi ça serait utile dans votre cursus. C'est un module choisi ou c'est un tronc commun? Ok. Bon. Et le Python, vous en avez déjà fait, mais pas l'année dernière. C'est ok. C'est quoi l'objectif en fait, vous savez? Ouais, et puis
En fait, en disciplinaire, on permet
D'accord.
de voir un peu le client.
Ok, ok. Pour essayer d'adapter la prochaine, parce que je encore moins vendredi. Bah, très bien. Du coup, en ligne, vous avez des questions? Pas? Tout le monde parle français. Do you have questions online?
No, thank you.
Okay. Well, then, have a good evening and see you see you on Friday. Bye bye.
You.